Welcome to For Science Salah Lotfy channel, where science meets curiosity. في هذه القناة لا نكتفي بعرض الأبحاث العلمية، بل نترجمها إلى المعرفة التي تصل إليك أينما كنت. Our mission is to make global scientific research understandable, accessible, and multilingual. جميع الفيديوهات العلمية هنا مترجمة إلى اللغة العربية، بالإضافة إلى لغات عالمية أخرى. French, Spanish, German, Urdu, and more. Because science speaks every language. نعم، العلم يتحدث بكل اللغات، ونحن نحرص أن يصلك بلغتك. If you're passionate about science, you're in the right place. اشترك الآن وابدأ رحلتك مع العلم خطوة بخطوة. For Science Salah Lotfy channel, العلم للجميع.
Welcome to For Science Salah Lotfy channel. Today we introduce an exciting and vital scientific topic that directly connects nuclear technology, materials science, and environmental protection. The focus of this episode is on the innovative development of lead borate glass systems doped with rare earth and transition metal ions. These advanced glasses are designed not only as efficient radiation shields but also as reliable containers for immobilizing radioactive wastes. Radioactive waste management is one of the greatest challenges facing nuclear power and nuclear medicine. The safe storage, handling, and transportation of these hazardous materials require containers with excellent radiation shielding ability, chemical durability, and structural stability. Traditional shielding materials such as concrete or heavy metals have many limitations. They are bulky, costly, and not always suitable for modern applications. This is where glass-based materials, particularly lead borate glasses, offer a revolutionary alternative. In the studies carried out by Professor Dr. Eman Abou Hussein, Radiation Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, together with Professor Dr. Madbouly, Radiation Safety Department, Nuclear and Radiological Safety Research Center, 3 types of lead borate glasses were fabricated. These glasses contain different amounts of lead oxide, 50, 35, and 15 mol%, and were doped with cerium, antimony, or manganese ions. What makes this research outstanding is the comprehensive testing under very high doses of gamma radiation, up to 250 kQi. The results showed that these glasses maintain their structure, density, and chemical durability even under such extreme conditions. In fact, their surfaces became smoother and more compact after irradiation, which is a surprising and highly promising result. Advanced characterization techniques including FTIR and ESR spectroscopy, scanning electron microscopy and Monte Carlo simulations, MCNP5 and Phi-X/PSD, confirmed their exceptional radiation shielding performance. Key parameters such as the mass attenuation coefficient, linear attenuation coefficient, half-value layer, and 10th value layer all demonstrated that these glasses are highly effective in blocking ionizing radiation. Among the tested systems, cerium-doped lead borate glass exhibited the best performance thanks to the unique ability of cerium ions to switch between Ce3+ and Ce4+ states. This property allows them to absorb defect centers and stabilize the glass network, making it more resistant to radiation damage. Similarly, antimony and manganese ions contributed to compact and stable glass structures, further enhancing the shielding properties. But beyond the scientific excellence, the economic significance of this research is equally impressive. These glasses can serve as a cost-effective and lightweight alternative to traditional shielding materials. They can be fabricated locally with relatively simple technology, reducing reliance on imported materials. Their potential applications are broad: containers for immobilizing high-level radioactive waste, shields in nuclear medicine departments and hospitals, barriers for industrial and research facilities working with radiation, even specialized uses in veterinary and dental radiology. By providing safer, more durable, and economically viable materials, this research contributes directly to environmental protection, worker safety, and the advancement of nuclear technology. It also demonstrates the ability of Egyptian scientists to deliver world-class innovations in material science with global impact. In this episode, we will explore how these radiation shielding glass systems work, why they are superior to traditional materials, and how they can transform the way we deal with radioactive waste management. Stay tuned as we dive deeper into the science, the technology, and the promising future of lead borate glass systems for nuclear applications, here on For Science Salah Lotfy channel. Welcome to For Science Salah Lotfy channel. In today's episode, we present a very special case where 2 scientific studies published in 2 different journals in 2 consecutive years are brought together in one unified topic. These studies were conducted by two distinguished professors from two different research centers, both under the umbrella of the Egyptian Atomic Energy Authority. The first study, titled Chemical and Radiation Shielding Effectiveness of Some Heavy Metal Oxide Glasses for Immobilizing Radioactive Wastes, was received in February 2023, revised in August, accepted in September, and published online on September 20, 2023, in the Journal of the Australian Ceramic Society. The second study, titled Fabrication and Characterization of Different PBO Borate Glass Systems as Radiation Shielding Containers, was received in November 2023, accepted in January 2024, and published online in February 2024 in Scientific Reports. Both studies converge on one critical theme: the development of lead borate glass systems doped with heavy metal ions such as cerium, antimony, and manganese, and their use as radiation shielding materials and immobilizers for radioactive wastes. The first researcher, Professor Dr. Eman Abou Hussein, from the Radiation Chemistry Department, National Center for Radiation Research and Technology, NCRRT, Egyptian Atomic Energy Authority, worked on understanding the chemical durability and structural stability of these glass systems under high doses of gamma irradiation. The results revealed that not only do the glasses remain stable, but their chemical resistance actually improves after exposure. This means they are well suited for containing radioactive materials for long periods, even in harsh environments. The second researcher, Professor Dr. Abou Madbouly from the Radiation Safety Department, Nuclear and Radiological Safety Research Center, Egyptian Atomic Energy Authority, expanded the scope by evaluating these glasses as radiation shielding containers. Using advanced techniques such as FTIR and ESR spectroscopy, along with Monte Carlo simulation codes like MCNP5, PHY-X/PSD, SRIM, and STAR, the study examined how these glasses perform against gamma rays, fast neutrons, and even charged particles such as protons and electrons. The findings from both studies are consistent and complementary. They confirm that lead borate glass systems doped with CESB or Mn ions show high structural stability under extreme radiation doses up to 250 kGy of gamma rays, improved density and compactness after irradiation, which enhances their shielding ability, excellent chemical durability, resisting corrosion in acidic, basic, and neutral media, outstanding shielding performance with high attenuation coefficients and low half-value and tenth-value layer thicknesses. Among all tested systems, C-doped lead borate glass stands out as the most effective, due to the ability of cerium ions to switch between Ce3+ and Ce4+, stabilizing the glass structure and absorbing defect centers created by radiation. From a practical perspective, this research has important economic and environmental implications. These glasses can serve as a cost-effective and lightweight alternative to traditional shielding materials, such as concrete and heavy metals. They can be fabricated locally, reducing costs and dependency on imports. Their potential applications extend to storage and immobilization of high-level radioactive wastes, shielding containers for radioactive materials in nuclear medicine units and hospitals, barriers in industrial research and healthcare facilities, specialized shielding in dentistry and veterinary medicine. By merging the results of these two consecutive studies, we can see a clear path toward developing innovative glass materials that combine scientific excellence, practical safety, and economic value. Together, these contributions by Professors Eman Abou Hussein and Abou Madbouly highlight the remarkable capacity of Egyptian scientists to advance nuclear materials research at an international level. In this episode, we will take a closer look at how these radiation shielding glasses were developed, the advanced testing methods used to prove their efficiency, and how they may shape the future of radioactive waste management and radiation protection. Stay tuned for this exciting journey, here on For Science Salah Lotfy channel. Welcome to For Science Salah Lotfy channel. In this episode, we bring together the results of two complementary studies, published in consecutive years in two different journals, but united by a single goal: developing advanced glass systems to safely immobilize radioactive wastes and shield against harmful radiation. Both studies were conducted by two distinguished scientists from the Egyptian Atomic Energy Authority, Professor Dr. Eman Abou Hussein, Radiation Chemistry Department, National Center for Radiation Research and Technology, Professor Dr. Abou Madbouly, Radiation Safety Department, Nuclear and Radiological Safety Research Center, Together, their research highlights how carefully designed lead-borate glass systems doped with Ce, Sb, and Eman ions can provide innovative solutions for one of the most pressing challenges in nuclear science: radioactive waste management. The context. Why glass? Nuclear power has become essential in energy, medicine, and industry. But the nuclear fuel cycle inevitably generates radioactive waste. This waste is highly hazardous, difficult to handle, and extremely expensive to store safely. Conventional methods such as concrete shielding or metal containers often suffer from bulkiness, high costs, and long-term instability. Glass, however, offers unique advantages. Its amorphous structure allows it to host a wide range of elements, including radioactive ones. Glass is lightweight compared to concrete, stable under extreme conditions, and flexible enough to be shaped into specialized containers. Borosilicate glasses such as Pamela and Sun 68 have already been used internationally to immobilize high-level radioactive waste. The focus of the Egyptian research was to design lead-borate glasses, incorporating 50, 35, and 15 mol% PbO doped with cerium, antimony, or manganese ions. These heavy metal oxides increase density and polarizability, enhancing the glass's ability to absorb ionizing radiation. The experimental approach. The glasses were fabricated using the melting annealing method, producing samples that were then exposed to high doses of gamma radiation, 120 kGy in the first study, 250 kGy in the second. This extreme irradiation was chosen to test the structural stability, chemical durability, and radiation shielding performance of the glasses. Key characterization techniques included FTIR spectroscopy to probe the borate network structure, identifying BO3 and BO4 groups, ESR spectroscopy to detect free radicals and structural defects, SEM imaging to observe changes in glass surfaces, Monte Carlo simulations, MCNP5, Phi-X/PSD, SRIM, STAR, to calculate shielding parameters for gamma rays, neutrons, protons, and electrons. Major findings. The results were remarkable. 1. Density and structural stability densities ranged from 3.34 to 5.30 G per cubic centimeter, and increased after irradiation. FTIR spectra showed that the trigonal BO3 and tetrahedral BO4 units remained stable, supported by polarizable Pb2+ ions and doped metals. ESR results indicated minimal change, confirming high resistance to radiation damage. 2. Chemical durability. After leaching tests in water, acid, and alkaline solutions for 3 months, durability actually improved by up to 25% in C-doped glasses post-irradiation. SEM images revealed smoother, more compact surfaces, suggesting increased resistance to corrosion. 3. Radiation shielding efficiency. Calculated parameters such as mass attenuation coefficient, MAC, linear attenuation coefficient, LAC, effective atomic number, ZEF, and radiation protection efficiency, RPE%, showed excellent shielding capacity. The half-value layer, HVL, and 10th value layer, TVL, were reduced, meaning thinner glass layers can block radiation effectively. Among the tested glasses, C-doped lead borate consistently outperformed the others, showing the highest shielding parameters and lowest transmission values. 4. Extended simulations for protons and electrons, SRIM and STAR simulations confirmed that the glasses exhibit superior stopping power and reduced penetration depth. Dose rate calculations, USVH, and lifetime cancer risk assessments indicated these glasses perform better than many conventional shielding materials. Why it matters: economic and practical implications. The significance of this research goes beyond scientific achievement. Nuclear waste management. These glasses can immobilize radioactive isotopes, preventing leakage and reducing long-term storage risks. Radiation protection in healthcare. They can be used in nuclear medicine departments, shielding medical staff during radiation therapy. Industrial and research applications, suitable for laboratories, veterinary clinics, and even dental radiology. Economic advantage. Lightweight, durable, and locally producible, these glasses reduce reliance on imported shielding materials, lowering costs, and fostering self-sufficiency. The combined impact. By merging their efforts, Professors Eman Abou Hussein and Amal Madbouly demonstrated a full picture of how advanced glass systems can function as both waste immobilizers and radiation shielding containers. Their complementary approaches, one focusing on chemical and structural stability, the other on simulation and extended shielding evaluation, together form a comprehensive framework for applying glass in nuclear technology. This collaboration underscores not only the scientific capability of Egyptian researchers, but also the strategic importance of investing in innovative materials to address global challenges in nuclear energy and radiation safety. We explored how two pioneering studies, carried out under the Egyptian Atomic Energy Authority, converged to show that lead borate glasses doped with Ce, Sb, and Men ions are among the most promising materials for radioactive waste immobilization and radiation shielding. Their scientific rigor, practical relevance, and economic feasibility make them a powerful alternative to conventional shielding solutions. Stay with us as we dive deeper into the details of these studies and their potential applications, right here on For Science Salah Lotfy channel. Welcome to For Science Salah Lotfy channel. In today's episode, we highlight a remarkable scientific achievement where two consecutive studies, carried out by two distinguished Egyptian scientists under the Egyptian Atomic Energy Authority, were combined into one comprehensive theme. Our focus is on lead borate glass systems doped with cerium, antimony, and manganese ions. These advanced materials were designed, prepared, and thoroughly characterized as radiation shielding glasses and immobilizers for radioactive wastes. The two researchers behind this work are Professor Dr. Eman Abou Hussein, Radiation Chemistry Department, National Center for Radiation Research and Technology. Professor Dr. Madbouly, Radiation Safety Department, Nuclear and Radiological Safety Research Center. Together, their efforts provide a unified picture of how glass materials can play a crucial role in nuclear safety, environmental protection, and medical radiation shielding. 3 different lead borate glass systems were prepared using the melting annealing method, a standard but highly controlled technique. High-purity raw materials were carefully selected, including H3BO3, PBO, K2CO3, Na2CO3, Al2O3, CEO2, Sb2O3, and MnO2, all supplied with 99.9% purity. The preparation steps were as follows. 1. 3 separate batches were weighed with high precision, corresponding to the desired glass compositions. 2. Each batch was ground into fine powders and melted in porcelain crucibles at 950-1100 degrees Celsius for 90-130 minutes, with gentle stirring every 30 minutes to ensure homogeneity. 3. The molten mixtures were cast into preheated stainless steel molds, then transferred immediately into annealing furnaces at 350-400 degrees Celsius. 4. Annealing for 1 hour removed thermal strain and internal stresses. Afterward, the samples cooled slowly at a rate of 30 degrees Celsius per hour, resulting in bulk glasses of approximately 3 mm thickness. This careful process produced 3 glass compositions containing 50%, 35%, and 15% PBO, each doped with Ce, Sb, or Mn ions. To evaluate these glasses, an extensive set of techniques was applied, both before and after exposing the samples to very high doses of gamma radiation. X-ray diffraction, XRD, confirmed the amorphous glassy nature of the samples. FTIR spectroscopy revealed the structural roles of trigonal BO3 and tetrahedral BO4 groups, as well as the effects of Pb2+ and the doped metal ions. ESR spectroscopy examined defect centers and free radicals created during irradiation. Scanning electron microscopy, SEM, captured surface morphology, highlighting changes after long-term leaching and radiation. Density measurements were taken using Archimedes' principle, showing small but significant increases after irradiation. Gamma-ray spectrometry with NAITL detectors quantified attenuation at energies of 662, 1173, 1275, and 1333 keV from C's 137 Co60 and Na22 sources. Additionally, Monte Carlo simulations, MCNP5, Phi-X/PSD, SRIM, and SSTAR, were employed to predict and validate radiation shielding performance under gamma, neutron, proton, and electron exposure. The results of these detailed experiments were impressive. 1. Density and structure densities ranged between 3.34 and 5.30 G per cubic centimeter, and increased slightly after irradiation. FTIR and ESR confirmed strong structural stability even after exposure to 120 kGy and 250 kGy of gamma radiation. 2. Chemical durability leaching tests in water, 0.1 NaHCl, and 0.1 NaOH over 3 months showed improved durability after irradiation, particularly in cerium-doped glasses, which improved by about 25%. SEM images revealed smoother, more compact surfaces after irradiation, indicating greater resistance to corrosion. 3. Radiation shielding efficiency. Experimental and simulated results for MAC, LAC, ZEF, RPE%, HVL, and TVL demonstrated strong shielding capacity. C-doped glasses consistently showed the highest shielding performance, with higher attenuation coefficients and lower HVL and TVL values. Simulations also revealed effective shielding for fast neutrons, protons, and electrons, validating the wide applicability of these glasses. 4. Health and safety implications. Dose transmission values and lifetime cancer risk estimates confirm the safety potential of these materials for radiation workers. Compared to conventional shields, the glasses provided lighter, more efficient, and cost-effective protection. The implications of this research are profound. Nuclear waste immobilization. These glasses can stabilize and contain high-level radioactive waste safely over long periods. Healthcare applications. They can serve as shielding containers in nuclear medicine units, protecting doctors and staff from harmful exposure. Industrial and research facilities. Useful in laboratories, radiological industries, veterinary clinics, and dental radiology units. Economic advantage. Locally producible, these glasses reduce dependency on imported shielding materials, lowering costs while creating opportunities for technological self-reliance. By uniting the work of Professor Eman Abou Hussein and Professor Madbouly, we see a complete picture. One study emphasizes the chemical and structural integrity of lead borate glasses under extreme irradiation. The other highlights their comprehensive shielding performance, confirmed through both experiments and advanced simulations. Together, these complementary results demonstrate that CE, SB, and Eman-doped lead borate glasses are not just laboratory curiosities, but practical, scalable solutions for the safe management of radioactive materials. In summary, the joint work of these two distinguished Egyptian professors shows that lead borate glass systems, doped with specific heavy metal oxides, can offer exceptional durability, superior radiation shielding, and significant economic value. This research is a milestone in nuclear material science, reflecting both global relevance and local innovation. Stay with us as we continue exploring the science, technology, and future applications of these groundbreaking materials, here on For Science Salah Lotfy channel. Welcome to For Science Salah Lotfy channel. In this episode, we present the combined results of two remarkable studies conducted by Professor Dr. Eman Abou Hussein from the Radiation Chemistry Department and Professor Dr. Madbouly from the Radiation Safety Department. Both are distinguished scientists under the Egyptian Atomic Energy Authority. Together, they explored how lead borate glass systems doped with cerium, antimony, or manganese ions can serve as highly effective materials for radiation shielding and radioactive waste immobilization. The first important result is that all the fabricated glass samples containing 50, 35, and 15 mol% PbO were confirmed to be amorphous. Unlike crystals, where atoms are ordered in repeating structures, these glasses showed broad humps without sharp peaks, a clear indication of their non-crystalline, glassy nature. FTIR spectroscopy revealed that the fundamental building blocks of borate glass are trigonal BO3 and tetrahedral BO4 units. When doped with heavy metal ions like CeSb and Men, these groups rearranged to form a more compact structure. Lead oxide, PbO, played a dual role, sometimes as a network modifier, sometimes as a network former, strengthening the glass and creating structural units like PbO4 and PbO3 pyramids. Each doped ion contributed in a unique way to the structure and shielding performance. Cerium, Ce3+, Ce4+. With its ability to switch valence states, cerium created more connected bonds, stabilized defect centers, and relaxed the glass structure after irradiation. This explains why C-doped lead borate glass showed the highest radiation shielding efficiency. Antimony, Sb3+, acting as a glass network intermediate, antimony formed stable SbO3 trigonal units. Its heavy polarizable ions combined with Pb2+ provided strong resistance to electron liberation under irradiation. Manganese, Mn2+, M3+. As a transition metal with multiple oxidation states, manganese could adapt within the glass network as both a modifier and a former. This flexibility allowed it to absorb defect centers and maintain structural stability even under high gamma doses. After exposure to 120 kGy of gamma radiation, the FTIR spectra of all glasses showed almost no major changes in vibrational bands. This confirms their structural stability. Interestingly, O-related vibrations around 2890-2990 cm1, which were present before irradiation, disappeared afterward. This means fewer non-bridging oxygens were formed, and the BOB bonds became more connected, making the glass network stronger and more resistant to radiation damage. One of the most striking findings was in chemical durability tests. Glass samples were immersed for 3 months in 3 solutions: distilled water, 0.1 NaHCl, and 0.1 NaOH. These experiments simulated conditions similar to geological repositories for nuclear waste. The results showed CE and SB glasses with higher PBO content displayed significantly greater durability than MN glass. HCl was the most corrosive medium for CE and SB glasses, while NaOH was more corrosive for MEN glass. After irradiation, the chemical durability of C-doped glass improved by about 25%. This is a remarkable discovery. It means gamma irradiation actually made the glass stronger against corrosion. This improvement can be explained by the formation of protective leached layers on the glass surface, colloidal gelatinous hydroxides that slowed further ion exchange. Monte Carlo simulations and experimental results confirmed excellent radiation shielding properties. High mass and linear attenuation coefficients, MAC and LAC. Low half-value and tenth value layers, HVL and TVL, meaning less material is needed for effective shielding. Higher radiation protection efficiency, RPE%, for C-doped glass compared to SB and MEN systems. In addition, the presence of heavy Pb2+ ions, along with the specific roles of CE, SB, and MEN, enhance the glass's ability to block gamma photons and reduce radiation transmission. These results have significant implications. Nuclear waste immobilization. The glasses provide a long-term solution for stabilizing radioactive waste, reducing the risks of leakage and environmental contamination. Healthcare applications. They can be used in nuclear medicine facilities to protect workers from gamma radiation exposure. Industrial and research facilities. Lightweight, durable, and efficient, they are ideal for radiation shielding in laboratories and radiological industries. Economic value. Locally produced in Egypt, these glasses can replace imported shielding materials, lowering costs and advancing self-sufficiency in nuclear technology. By combining the efforts of Professor Dr. Eman Abou Hussein and Professor Dr. Madbouly, we get a comprehensive understanding of how these glass systems behave under extreme conditions. One aspect highlights structural and chemical stability after irradiation. The other emphasizes shielding efficiency and health safety applications. Together, they form a complete story. Lead borate glasses doped with CE, SB, and Eman are not only scientifically robust but also practical and economically viable solutions for managing nuclear waste and protecting people from radiation. In summary, these studies show how advanced material science can directly address one of the world's most urgent challenges: radioactive waste management. The combination of Egyptian scientific expertise, innovative design, and rigorous testing has produced glass systems that are stable, durable, and efficient under extreme radiation conditions. Stay tuned as we explore more about how science and technology continue to open new pathways for a safer and more sustainable future, only here on For Science Salah Lotfy channel. Welcome to For Science Salah Lotfy channel. Today's episode brings together the detailed findings of 2 important studies from the Egyptian Atomic Energy Authority, conducted by Professor Dr. Eman Abou Hussein and Professor Dr. Madbouly. Their research explores how specially designed lead borate glasses doped with rare earth intermediate and transition metal ions can act as effective materials for radiation shielding and nuclear waste immobilization. Corrosion and durability studies. One of the most critical aspects of these materials is their chemical durability. To test this, the researchers immersed glass samples in distilled water, hydrochloric acid, and sodium hydroxide solutions for a full 3 months, both before and after exposure to a massive dose of 120 kGy gamma irradiation. The results were striking. Cerium-doped glass showed the highest resistance to leaching, losing far less weight compared to the other glasses. Antimony-doped glass also showed improved durability due to the combined effect of Sb3+ and Pb2+ ions, which formed a closed and relaxed network, reducing ion migration. Manganese-doped glass, though less durable due to lower PBO content and the presence of mobile sodium ions, still benefited from irradiation, which helped stabilize the structure. Overall, the effect of irradiation was surprisingly positive. Instead of weakening the glasses, gamma rays actually increased their durability by about 25% for CE glass, 4% for SB glass, and up to 10% for MN glass. This improvement is attributed to bond rearrangements, energy release, and healing of defect centers within the glass network, which reduced ion exchange and enhanced structural compactness. The special contribution of each ion explains these results. Ce3 plus C4 plus ions balance negative charges in tetrahedral units, stabilize the structure, and help absorb radiation-induced defects. Sb3 plus ions like Pb2 plus participate in the network, but with less tendency to convert BO3 into BO4. Still, the presence of both heavy ions strongly blocks electron passage and reduces leaching. Mn2 plus M3 plus ions act as redox partners, adapting flexibly within the glass to absorb defect centers and strengthen the network. Density measurements further confirmed these findings. Glasses with higher PbO content had higher density values, as heavy lead atoms replaced lighter boron atoms, compacting the structure and improving both durability and shielding efficiency. Surface morphology, SEM analysis. Scanning electron microscopy provided another layer of evidence. Before irradiation, glass surfaces showed roughness, cavities, and non-uniform leached layers, particularly boron-rich regions. After irradiation, the surfaces appeared smoother and more homogeneous. This clear visual proof supported the idea that irradiation helped create a denser, more stable, and more durable network. Radiation shielding parameters. Beyond durability, the most important role of these glasses is radiation shielding. Researchers analyzed shielding performance through both experiments and simulations using Monte Carlo codes and PHY-X/PSD software. Several parameters were measured. Linear attenuation coefficient, LAC, decreased with increasing photon energy, but was highest for CE glass due to its density and PbO content. Mass attenuation coefficient, MAC. At very low energies, CE glass again showed the best performance thanks to the dominance of the photoelectric effect. Effective atomic number, ZEF, highest in CE glass, confirming superior shielding at energies dominated by photoelectric interactions. Half-value layer, HVL, and 10th value layer, TVL, CE glass required the least thickness to block radiation, making it the most space-efficient shield. For example, at 662 keV, the HVL of CE glass was 26% lower than SB glass and nearly 50% lower than MEN glass. Mean free path, MFP, shortest for CE glass across all photon energies, showing its superior attenuation ability. Radiation protection efficiency, RPE percent. CE glass achieved up to 63% efficiency at low energies compared to 50% for SB and only 34% for MN glass. These results consistently rank the glasses as G1, CE, G2, SB, G3, MEN in terms of shielding performance. Comparison with standard materials. How do these glasses compare to conventional shielding materials like lead, PVC composites, or other borate glasses? At 662 keV gamma energy, the studied glasses displayed better or comparable MAC, ZEF, and HVL values. While they are slightly lighter than pure lead, their reduced toxicity, improved durability, and tunable composition make them more attractive for practical use. The heaviness percentage comparison showed lead at 100%, CE glass at 54.9%, SB glass at 43.6%, and MEMN glass at 32.5%. This makes them significantly lighter while still maintaining strong shielding efficiency, an advantage in applications where both weight reduction and safety are critical. Practical significance. The findings open the door for multiple applications. Nuclear waste immobilization, highly durable and chemically stable. These glasses are ideal containers for long-term storage. Healthcare. They can be used in nuclear medicine and diagnostic imaging facilities to shield staff and patients from harmful radiation. Industrial and research facilities. Their lighter weight compared to lead makes them practical for designing compact, efficient radiation barriers. In conclusion, the combined work of Professor Dr. Eman Abou Hussein and Professor Dr. Madbouly demonstrates how advanced glass systems, especially those rich in PbO and doped with CE, SB, or MN, can achieve remarkable radiation shielding efficiency, chemical durability, and structural stability, even under extreme irradiation. Their contribution highlights not only the scientific strength of Egyptian research, but also its practical value in solving global challenges like radioactive waste management and radiation protection. This is the power of material science applied to real-world problems. Stay tuned for more deep scientific insights, only here on For Science, Salah Lotfy channel. Welcome to For Science Salah Lotfy channel. In this episode, we bring together the research of Professor Dr. Eman Abou Hussein and Professor Dr. Madbouly, two distinguished scientists from the Egyptian Atomic Energy Authority, who worked in two different research centers but on the same fascinating subject: the design of lead borate glass systems doped with heavy metal ions for radiation shielding and nuclear safety applications. To understand these glass systems, the researchers relied on FTIR spectroscopy, one of the most powerful tools to analyze both crystalline and amorphous materials. Unlike crystals, glasses do not have long-range order. Instead, their atoms are arranged in random, interconnected networks. The Borate network in particular is built from two main units: trigonal BO3 units, which can connect to form boraxol rings; tetrahedral BO4 groups, which increase when network modifiers like lead, cerium, antimony, or manganese are added. When these modifier ions enter the glass structure, they break BO-B bonds, creating non-bridging oxygens, and transforming some BO3 units into BO4 groups. This process depends on the type and amount of the added ion. What makes lead oxide, PbO, unique is that it acts both as a modifier and a former. At lower concentrations, Pb2+ balances charges and helps form BO4 units. But as its concentration increases, Pb2+ also forms its own structural groups, such as PbO4 or PbO3 pyramids, strengthening and compacting the network. When the FTIR absorption spectra of three different glasses, doped with Ce, Ab, and Min, were recorded before and after exposure to 250 kGy of gamma radiation, the results were impressive. Despite the extreme irradiation, the spectra showed almost no significant changes in band positions or intensities. This stability indicates that the glass networks remain strong and compact, resisting the disruptive effects of ionizing radiation. Some key features observed included: 1. Bands at 445-460 cm1 linked to vibrations of Pb2+ building units. 2. Broad bands around 570-610 cm1, corresponding to Ce, Sb, or Eman vibrations in the network. 3. A band at 680-708 cm1 from BOB linkages. 4. Sharp bands at 940-960 cm1 linked to BO4 stretching vibrations. 5. Strong bands in the 1200-1400 cm1 range associated with diborate and pentaborate groups. 6. Broad bands between 1600-4000 cm1 reflecting hydrogen bonding and OH vibrations. Together, these spectra revealed the robust structural integrity of the glasses, even under massive radiation doses. Looking closer at the deconvoluted spectra gave insights into how each ion contributed. Cerium-doped glass, CpBO-B2O3. Cerium exists in both Ce3+ and Ce4+ states, switching between them to stabilize charges and absorb defects. After irradiation, the spectra revealed decreased absorbance intensities near 800 cm1, suggesting the formation of more bridging bonds and a more relaxed, stable structure. This makes C-doped glass particularly radiation resistant. Antimony-doped glass, SbPbO-B2O3. Sb2O3 acts as a network intermediate. Some Sb atoms form BO4 units, while others remain as SbO3 pyramids. The presence of heavy Sb3+ and Pb2+ ions prevented the free passage of electrons generated by radiation, leaving the network largely unchanged. Only small shifts in peak positions were seen, confirming remarkable shielding stability. Manganese-doped glass, MnPbO-B2O3. Manganese is highly versatile, existing as Mn2+, Mn3+, or Mn4+. This flexibility allows it to absorb radiation-induced defect centers by switching oxidation states. After irradiation, Mn glass spectra shifted slightly to lower wave numbers, but overall the vibrational bands remained stable, indicating a rigid and compact structure capable of effective shielding. The researchers also studied N4, the fraction of 4 coordinated boron atoms. This parameter is crucial in assessing the balance between BO3 and BO4 groups. For C glass with 50 mol% PbO, N4 decreased after irradiation, suggesting that the structure became even more stable and relaxed. For Sb and Men glasses, N4 values showed a slight increase, but the networks remained largely intact. This analysis confirmed that higher PbO content leads to greater structural stability, with C glass again performing the best. Density is another key property. Before irradiation, the glasses had densities of 5.26 G per cubic centimeter, for C glass, 4.25 G per cubic centimeter for Sb glass, and 3.34 G per cubic centimeter for Mn glass. These values correlate directly with PbO content, since heavier lead atoms increase the compactness of the structure. After irradiation, densities rose slightly, further proving that gamma rays compacted the structures instead of damaging them. This compactness enhances both durability and shielding efficiency. The combined work of Professors Eman Hussein and Eman Madbouly demonstrates that lead borate glasses doped with CESB and Eman are not only structurally stable under extreme radiation, but also chemically durable and highly effective as shielding materials. These glasses can serve as immobilizers of radioactive waste thanks to their chemical resistance. Radiation shielding containers, lighter and safer than traditional lead. Protective barriers in nuclear medicine, research labs, and industrial facilities. By merging insights from two separate but complementary studies, we see a unified picture. Innovative glass systems that can withstand radiation, resist chemical attack, and protect humans and the environment. This remarkable research from Egypt highlights how advanced material science can directly address global challenges in nuclear safety and radiation protection. Stay with us as we continue exploring such breakthroughs, here on For Science Salah Lotfy channel. Welcome to For Science Salah Lotfy channel. In today's episode, we continue exploring the groundbreaking research of Professor Dr. Eman Abou Hussein and Professor Dr. Amal Madbouly from the Egyptian Atomic Energy Authority. Their work unites material science, radiation chemistry, and nuclear safety, focusing on lead borate glass systems doped with cerium, antimony, and manganese ions. These advanced glasses are being developed as radiation shielding containers and potential hosts for radioactive waste immobilization. One of the first indicators of shielding efficiency is density. As shown in their results, glass density increases with higher PBO concentrations. G1, highest PBO, reached the greatest density, followed by G2 and G3. After exposure to a massive 250 kJ gamma dose, densities actually increased slightly, indicating that irradiation compacted the structure rather than damaging it. This behavior highlights the remarkable radiation stability of these glasses. To probe structural changes at the atomic level, the team used electron spin resonance, ESR. ESR is highly sensitive to free radicals created by ionizing radiation. Surprisingly, after 250 kJ gamma irradiation, the spectra of all three glasses showed no sharp ESR signals. This means that almost no free radicals were formed. The glass networks resisted radiation damage. The minor asymmetry between spectra was simply due to differences in ion composition. The conclusion was clear. These glasses form a highly stable blocked network where radiation photons lose energy without creating defects. This is exactly what we want in a shielding material. Monte Carlo simulations revealed how effective these glasses are at shielding gamma sources, specifically Cs, 137 at 662 kV, and F18 at 511 kV. At 1 m distance with 1 cm thickness, dose rates were highest. At 3 m distance with 2 cm thickness, dose rates dropped dramatically. This follows the Alara principle. As low as reasonably achievable. Distance and shield thickness are both crucial. Importantly, the shielding efficiency ranked as G1, G2, G3, in direct correlation with PBO content and density. Another way to measure effectiveness is dose transmission percent, how much of the original dose passes through the shield. At 662 kV, transmission through G1 dropped from 26.9% at 1 cm to just 21.5% at 2 cm. At 511 kV, it dropped even further, from 8.9% to 6.4%. G2 and G3 had higher transmission values, proving them less efficient than G1. These numbers make it clear. Denser glasses with more PBO absorb more photons, lowering dose transmission and protecting workers more effectively. Radiation shielding isn't just about physics, it's about protecting people. The researchers calculated the excess lifetime cancer risk for workers exposed 2,000 hours per year over 40 years. Results showed G1 reduced lifetime cancer risk the most, outperforming many previously studied shielding glasses. G2 and G3 were less effective than G1, but still better than other common glass shields like Z-B and BI-10. This underscores the direct health and safety benefits of these advanced materials. Radiation protection must also consider charged particles like electrons and protons. Using Monte Carlo simulations with E-star, the team studied mass stopping power, DEDX, and range, CSDA for electrons, projection range for protons. Findings included, for electrons, stopping power decreased as energy increased, but G1 always performed best, offering the highest energy absorption. For protons, G1 again delivered superior protection with the shortest penetration range. These results confirm that PBO-rich glasses are not just effective against gamma rays, but also against charged particle radiation, broadening their protective role. Finally, the team evaluated fast neutron attenuation using Phi-X/PSD software. The results showed that while all three glasses had good neutron shielding properties, G1 compared favorably to standard materials like water, graphite, and concrete once thickness exceeded 2 centimeters. This means G1 glass is not only a strong gamma and charged particle shield, but also a competitive neutron attenuator, making it highly versatile for nuclear applications. By combining density analysis, ESR, dose transmission, lifetime cancer risk stopping power, and neutron shielding, these studies build a complete picture. G1 glass, C-doped, high PBO, is the most effective shield across the board. G2, SB-doped, and G3, MEN-doped, also offer strong protection but are less efficient than G1. All three glasses remain structurally stable even under extreme gamma doses, showing little to no defect formation. This research by Professors Eman Abou Hussein and Madbouly highlights the incredible potential of engineered glasses as safe, stable, and effective alternatives to traditional shielding materials like lead and concrete. Their work not only advances material science but also contributes directly to worker safety, environmental protection, and the sustainable future of nuclear technology. Stay tuned as we continue exploring the science behind nuclear safety, right here on For Science Salah Lotfy channel. Welcome to For Science Salah Lotfy channel. Today's episode highlights a remarkable collaboration of two leading scientists from the Egyptian Atomic Energy Authority, Professor Dr. Eman Abou Hussein and Professor Dr. Madbouly. Together they explored how specially engineered lead borate glasses doped with cerium, antimony, and manganese ions can become next-generation radiation shielding materials and safe containers for radioactive waste. Structural stability and FTIR findings. The research begins with the FTIR absorption spectra. All three glass systems, CE, SB, and MEN lead borates, showed consistent vibrational bands before and after exposure to intense gamma radiation, up to 250 kGy. C-doped glass benefited from cerium's ability to absorb radiation photons and stabilize defects. SB-doped glass showed stability thanks to the massive polarizable Sb3+ ions, which slow down liberated electrons. Eman-doped glass relied on transition metal ions and compacted ALO4 groups to capture defect centers. The disappearance of certain BOH bands after irradiation confirmed stronger BOB linkages, proving that these glasses actually become more compact and stable under radiation stress. Chemical durability. One of the most surprising results came from long-term corrosion tests. The glasses were placed in water, acid, and alkaline solutions for 3 months, even while under high radiation exposure. Instead of weakening, the glasses demonstrated enhanced chemical durability. For example, C-glass improved by about 25% after irradiation, with smoother, more compact surfaces observed under SEM. This means these glasses not only survive harsh environments but also improve in performance when exposed to radiation, a rare and valuable property. Shielding efficiency. The researchers also studied multiple shielding parameters, such as linear attenuation coefficient, mean free path, and half-value layer. At 662 keV gamma energy, C-glass G1 showed 19% better radiation protection than SB and MEN glasses. It had the lowest HVL and TVL values, meaning thinner layers could block more radiation. Simulations confirmed that higher PBO content leads to stronger shielding, with C-glass 50 mol% PBO outperforming SB 35% and MEN 15%. Health impact and worker safety. Shielding isn't only about physics, it's about people. When calculating excess lifetime cancer risk for workers exposed to radiation over 40 years, C-glass reduced the risk more effectively than many previously studied materials, including commercial biological shields. This makes it highly relevant for protecting staff in nuclear medicine units, hospitals, and other facilities where radioactive materials are routinely handled. Charged particles and neutron shielding. Beyond gamma rays, the glasses were also tested against electrons, protons, and fast neutrons using Monte Carlo simulations. Electrons. C-glass showed the highest stopping power, absorbing more energy before electrons could pass through. Protons. C-glass again delivered the best protection, with the shortest penetration depth. Fast neutrons. Its shielding ability compared favorably with common materials like water, graphite, and concrete when thickness exceeded 2 centimeters. This proves that these glasses are multi-purpose shields, capable of handling several types of radiation simultaneously. From structural stability and chemical durability to gamma, charged particle, and neutron shielding, these studies show that lead borate glasses with high PBO content, especially C-doped glass, are among the most promising candidates for radiation shielding and safe radioactive waste storage. The outstanding work of Prof. Eman Abou Hussein and Prof. AML Madbouly provides a scientific foundation for safer environments in nuclear medicine and radiation facilities, with potential global impact on health and environmental safety. Stay tuned for more scientific insights here on For Science Salah Lotfy channel. Welcome to For Science Salah Lotfy channel. Today's episode has focused on groundbreaking research carried out by two outstanding scientists of the Egyptian Atomic Energy Authority. Their work on lead borate glasses doped with cerium, antimony, and manganese demonstrated how innovative materials can provide structural stability, chemical durability, and effective shielding against radiation. The combined efforts of these researchers have proven that specially designed glass systems can withstand high doses of gamma radiation, maintain their chemical integrity in corrosive environments, and offer safer alternatives for radioactive waste storage and radiation shielding applications. Their findings are not only scientifically significant but also hold practical and economic importance, particularly for nuclear medicine units and radiation facilities where safety is paramount. At the end of this episode, I, Professor Dr. Salah Lotfy, professor at the Egyptian Atomic Energy Authority, would like to extend my sincere thanks and appreciation to the two distinguished researchers. Professor Dr. Eman Abou Hussein, Professor of Radiation Chemistry, National Center for Radiation Research and Technology, NCRRT, Egyptian Atomic Energy Authority. Professor Dr. Amal Madbouly, Professor of Radiation Safety, Nuclear and Radiological Safety Research Center, Egyptian Atomic Energy Authority. Your remarkable efforts and dedication in producing such high-value research are truly commendable. And to our viewers, I invite you to share your thoughts and comments on these important scientific studies in the section below the video. Your engagement helps us build a stronger scientific community and continue exploring research that matters. Thank you for watching and stay connected with us here on For Science Salah Lotfy channel.